Okay, this video will be dedicated to working a string of problems from your chapter 1 homework. And I'll start with number 2. Let's actually pull up the text and read through the problem statement itself. Number 2 is the one about this gal named Julie who wants to visit her grandma. That's sweet. Grandma lives 100 miles away. So on the way to grandma's house, she begins by driving half the distance at 40 miles per hour. So she drives the first 50 miles at 40 miles per hour, and then the other 50 miles she drives at 60. And in part A, we're supposed to figure out what's her average speed on the way to the house. Part B is subtly different. In part B, she's actually coming back from grandma's house, and this time she drives half of the time interval at 40. So the difference is going to be whether you drive half the time or half the distance at a given speed. The problem is it's mundane, right? It's not a very exciting question that's being posed here. And for that reason, you expect it to be easy. But it's a little trickier than you might expect. And I really need to get faster with pausing this as I switch between screens here. So let's start with part A. Part B we'll see is the easy part. They're asking for average speed. Well, remember, speed is the absolute value of velocity. So let's first calculate average velocity on the way there. And we know that the definition of average velocity would be the total displacement over the total time. As long as you remember that definition, you can't go too far astray in this problem. And as you're setting up these problems, it really pays off to pick clear notations. So since we're first told, we're told that she drives half the distance at 40 miles an hour, we're going to need the time it takes. Let's do this. I'll say T with no subscript. That'll be the total time. And we'll say T is equal to T1 plus T2. And I'm going to use the label T1 as the amount of time driven at 40 miles per hour. And T2 will be the total time driven at, what was it, 50 miles per hour? No, it was 60, pardon me. So I need to calculate these times individually so that I can add them up to find the total time. The average velocity for the entire trip requires knowing the total time. Well, for constant speed, if your speed's constant, then you can go ahead and use this old relation that you've known, the common sense relation that you've known forever. Distance equals speed times time. And let's solve that for time. So all we have to do is divide the two speeds into the distances to find how long she spends driving at those speeds. So time 1, the time spent driving 40 miles an hour, we'll take the distance of 50 miles, and into that number we will divide 40 miles per hour. And when you write it this way, instead of MPH, it has the advantage of showing you the dimensionality. The miles will cancel and the hours will come up top. And rather than put that as a decimal, I'm just going to write that as 5/4 of an hour. You see, and I'll try to write bigger here, if you picked easy numbers, you would do the stuff in your head. It would be common sense. Like, what if you had to drive 50 miles and you did so at 25 miles per hour? It's easy to see that you're going to have to drive for 2 hours if you're going 25 miles per hour, but you have to go 50 miles. When you pick numbers that aren't easily divisible, you kind of have to write stuff down. Okay. T2, she goes another 50 miles. And she does so at 60 miles per hour. The zeros cancel, and I will write that as 5/6 of an hour. This is much like how your solutions manual does it. And so now we can say that the average trip, or the average velocity, for the whole trip would be the total displacement, which is 100 miles. She's got to go 100 miles total, divided by the total time. And what I'll do is enclose the sum of the numbers in parentheses and put the units outside. So I'll say 5/4 plus 5/6 of an hour. Okay, well, that's 100 miles. And of course, you could just put this in your calculator, but I'd like to add these numbers with the common denominator. I think the lowest common denominator would be 12, right? So to make this fraction into a fraction with 12 as the denominator, I'd have to multiply on top and bottom by 3. So this would give me 15 up top. And then here I'd have to multiply on top and bottom by 2. So 15 plus 10 twelfths of an hour. And is there an easier way to do this that I'm overlooking? Possibly. Okay, so well, the 12 in the denominator of a denominator is like a 12 out front. So that's 100 miles, 25 hours. Great. Okay, so 100 divided by 25 is 4 times the 12 gives us 48 miles per hour. And we see already that our first guess would have been incorrect. If you had thought, well, half the distance at 40, half at 60, the average speed must just be the number right in the middle. That's no good here, because if you look back at a previous video, I talked about how if you look at a plot of, what was it, velocity versus time? Yeah. Here's an arbitrary plot of velocity versus time. The area under that curve is the displacement. So if we go up here to the definition of average velocity, if you took the total displacement, which is the area under this curve, and divided it by delta t, which is the time interval, that's the base here, that would give you the height of some equivalent rectangle. And evidently the height of that equivalent rectangle here is not 50, it's 48. I can go one step further. If she drives half the distance at 40 and half the distance at 60, at which speed does she spend more time driving? Isn't it going to take her longer to drive the first 50 miles at 40 miles per hour than it'll take her to drive the last 50 miles at 60 miles per hour? She's going to spend more time at 40. So how about I exaggerate the difference there? Here's a graph of her velocity versus time. Let's just suppose that when she's driving 40, she's going to have to drive for quite a while to cover those 50 miles. And then she jumps up to 60, obviously not to scale, and that's a much briefer trip because of the greater speed. The area under that curve represents her distance traveled. And we know that total velocity is total distance over total time, where total time is the base here of this geometric shape. So do you see that the height of the equivalent rectangle is not going to be halfway between 40 and 60? It's probably more like this. And I've grossly exaggerated the difference in the times T1 and T2 here just to help you see that. Okay, part B is simpler because now we're told that she really does spend half the time at 40 and half the time at 60 miles per hour. So your solutions manual does it one way. Here's a more direct way to do it. Let T again equal the total trip time. I should say the total return trip. This is her on the way back from Grammy's house, total return. And that's a long way to drive to visit your grandma. Good for her. Total return trip. Time. All right, and I'm going to simply solve this in one line. Watch this. The distance she covers while going 40 miles per hour, well, that would be 40 miles per hour times T over 2, right? Because I'm using the letter T as the total return trip time, and we're told that she drives for half of that time at 40 miles per hour. So 40 miles per hour times 1/2 of the unknown total trip time, that would be part of the journey back. The rest of the journey is covered by going 60 miles per hour or for a time of T over 2. So I don't actually know what this distance is because I don't know what the time is yet. I could call this D1 and D2, but it's really unnecessary because don't we know that the sum of these two distances has to equal the 100 miles to get back home? So this might be the most direct way to solve for T. And one way to do this would be to multiply the whole equation by 2. That cancels the 2's in the denominators. So we'd have 40T plus 60T equals 200. 100 times the time would be 200. And now it's evident that the time is merely 2 hours. And now we can go ahead and use this definition for average velocity again. The total displacement was 100 miles. She had to drive 100 miles to get home, but she did so in 2 hours. And now the velocity really is the arithmetic mean of the two speeds. It's 50 miles per hour. Could we also see that graphically? Sure, because if you make, you know what, I don't want to spoil this pristine piece of paper here. So I'll use some junk notes from last semester. We draw the graph of velocity versus time for the return trip. Well, let's say this is 40 miles per hour and up here is 60. Now she really does spend equal times at the two speeds. So I'm extending this out the same distance. So this is half the return time, the other half of the return time. And we're looking for the height of the equivalent rectangle. And I'm sure you can see that because this is the same distance as this, or the same time interval, the rectangle that has the same area as the area under the V versus T curve would have to be the rectangle with a height of 50. So you can also just answer that graphically. Now, if you understood that problem, you're probably equipped to solve one of these teaser problems presented by, I think his name is Derek Muller, the host of the Veritasium YouTube channel. So let's go to his channel and take a look at one of these brain teasers. The name of this video from the Veritasium channel is 4 Revolutionary Riddles, and then each of the riddles is explained in a subsequent video. If you want to find that one, you just type in 4 Revolutionary Riddles Explained.
3, 2, 1.
Number 3, I want you to think about running 2 laps of this track. Now the first lap you can go as slowly as you like. Let's call that speed V1. But on your second lap, I want you to run faster, such that the total average speed for both laps combined is twice V1, twice the speed of your first lap. So the question for you is, how fast do you have to run that second lap so that your total average speed is 2 V1? Number
I just spent 5 minutes explaining that problem. Come to find out, I forgot to hit record. Arr. So let's try that again. I'll be very procedural in setting up the solution, this first method, and then we'll go back and see if we can just reason through it directly. But I'll start by using the letter D for the track length. So each lap, this person would have to run a distance D. I'll use the label T1 for the time to run the first lap. And of course, T2 would then be the time for the second lap. I think it's clear that V1 would be the speed at which this person has to, or by assumption, they ran the first lap at a particular speed, V1, and V2 is the required speed to run the second lap. Now we know that the average overall speed is the total displacement over the total time. That's our general formula for average velocity. But for this particular problem, the total distance would be 1 lap plus the second lap. That's a distance of 2D. And the total time would be the time for the first lap plus the time for the second lap. And we're going to require that, or allow, what's the word I'm looking for? I'll just say let the average velocity turn out to be double the velocity around the first lap. That was the way the problem was stated. How fast do you have to run that second lap to bring your average velocity up to double the velocity at which you ran the first lap? Well, since we've already used this formula relating distance and time, I'm just going to quote it. This is applicable as long as your velocity, that's garbage, what am I doing? Distance equals velocity times time. As long as your speed is constant, you can go ahead and use this, solve this for t, you get d over v. I'm going to use that to evaluate these 2 times. So the average velocity needs to be 2 times the velocity for lap 1. I'm evaluating this as such. Well, that would be the total distance over the total time. And time 1 would be distance 1 over speed 1. And time 2 would be distance 2, also the track length, divided by speed v2. And we're solving this for v2. we want to use this equation to figure out what V2 has to be in order to bring the average velocity for the entire thing up to 2 times V1. Well, first, let's recognize we can get rid of the 2 on both sides. Maybe you recognize also we could just divide out D. To make that clearer, I'll multiply on top and bottom by 1 over D, so that I'm actually multiplying by the number 1. I'm not changing anything. So now the numerator becomes 1. When I distribute the 1 over D, each of these D's also goes away, and I'm left with V1 equals 1 over the reciprocal of V1 plus the reciprocal of V2. Again, we're trying to get at V2. So let's multiply on top and bottom by V1 over V2. And I find this, V1 equals the product of the speeds over, and when I distribute the denominator here to both of these terms, you should find that I get V2 plus V1. We're getting closer here. How about I multiply on both sides by this denominator? I'd have V1 times V2 plus V1 equals V1 V2. And I'll go ahead and distribute. I find that V1 V2 plus V1 squared has to equal V1 V2. And now you may immediately recognize, wait a minute, I could just subtract this from both sides, and that would say that V1 squared would have to be 0? What? The mic probably cut out there. I shouldn't yell. Well, what if V1 wasn't 0? You know, what if you ran your first lap at 10 miles per hour and you want to get your average speed for the whole trip up to twice that? Well, maybe you're already thinking, that's suspicious. How could you bring your average velocity all the way up to 20 miles per hour when it's difficult to even run 20 miles per hour at all? So there's something funky going on here, right? Another way to do this would be, how about I subtract this from both sides, but don't actually, cross it out. So I would have this V2 times V1 minus V1. I've just moved this over here, and I've factored out V2. Well, V1 minus V1 is 0. So V1 squared equals V2 times 0. What? Any number times 0 is 0, right? Well, let's say you actually were going 10 miles an hour for the first lap. 10 squared is 100. What number times 0 could possibly give you 100? Well, this is kind of a sloppy discussion, but only infinity could do that, right? Only infinity times 0 could give you something that's not 0. So what the math is telling us is it's impossible to do this. There is no speed at which you could run the second lap to bring your average velocity for the entire run up to twice V1. Not possible. You could also just go ahead and solve this directly. When you divide by 0, you get something undefined, loosely speaking, infinity. Okay, so that's my solution. You should go on YouTube and check out the way he explains it. Here's another way of thinking about it. 2 times V1. Let me pause and make sure I know what I'm doing here. So this is kind of how Derek Mueller explains it in the video. We know that the correct expression for your average speed for the entire run would be the total distance, 2 laps, divided by the total time, where this is the time you spent at V1 and this is the time at speed V2. But remember, your speed V1 is the first lap distance divided by T1. We want this expression to be exactly twice this expression. You see there's already a factor of 2 here? So if I just cover up the T2, 2 times D over T1, that's exactly what we want. Because that would be 2 times V1. Does everybody see that? This is 2 times V1. So the only way to accomplish that is if this is 0. Right? There's no time left over to accomplish that average velocity. So the only way to do it is to run the second lap in a time of 0. That's equivalent to saying that you'd have to run it infinitely fast. Now, if you're like me, maybe you get a kick out of seeing people's comments on YouTube videos. So I scroll down under the video with the answers to the riddles, and I like this guy's answer. What if you just don't run either lap? Both laps are run at 0 velocity. 2 times 0 is, in fact, 0. See, there's some funny people out there on the internet. Next up is number 10 from chapter 2. As with many of these exercises, it refers to a graph that was presented in an earlier problem. So they're telling us to go back to problem 2.7 and look at the diagram for that one. And in this case, we're supposed to interpret the graph as a plot of blood velocity versus time. They're looking at blood going in and out of a part of your heart. And we're supposed to figure out what the acceleration is. So you should immediately be thinking velocity, acceleration, there's a relation there. We know that acceleration is the rate of change in time of velocity, and that would be the slope. So I go back up to problem 7. There's the diagram we want. And what are those words? Systolic, diastolic. There's 2 phases to your, I don't know much about the heart. But what's going on here? We would like to, I'm having technical difficulties here. We would like to measure the slope there. So let me just plot this in a PowerPoint. Here it is, velocity versus time. And because this curve here is really just 2 straight line segments, that will make it very easy to determine the slope. We just do rise over run. So in the first phase of the heartbeat, we can see that the velocity goes from 0 meters per second up to 0.8. So let me just implement the definition of acceleration as change in velocity over change in time. Remember, this is really an average velocity. Excuse me, this is an average acceleration. It's an average rate of change of velocity. But if your velocity is changing at a constant rate, then average is the same as instantaneous. Remember, what's the one curve that has a constant slope? That's a line, and that's what we're looking at here. So the velocity increases over this time interval here from 0.1 seconds to, this looks to be 0.15 seconds because it's halfway between 0.1 and 0.2. During that time interval, the velocity rises by 0.8 meters per second. That's why I emphasized a change of positive 0.8. And the time interval here is half of, see how each of these increments is 0.1? Well, half of that would have to be 0.05. Check out the units. They are, in fact, meters per second per second. So that's more than, oops, that's supposed to be a plus sign. Just ignore that. This is more than 1 G, right? That's kind of interesting that the blood in your heart is accelerating at about 1.5 Gs, 1.6 Gs. For the second phase of the beat, notice that the change in magnitude as we go from here to here, the velocity is changing again by 0.8, but this time it's decreasing. It's going back down to 0. So I put a delta V of negative 0.8, and the time interval is longer. In this case, it's 1.5 times the basic unit here of 0.1. So that's where the 0.15 came from. Okay, so it's just very simple application of the definition of average acceleration. I like this next problem. Number 15 from chapter 2. How many days will it take a spaceship to get up to the speed of light? First of all, not possible. Let me interject this real quick. Even if your spaceship was the size of a car, like a Volkswagen Rabbit, to get that thing up to like 99% speed of light, last time I checked, would take more energy than the United States uses in an entire year. Now, I didn't make that number up. If you take 3C, you can learn how to calculate that very simply. E equals mc squared is basically what I'm using. But getting anything with mass up to that speed, not very realistic. In any case, what if you could do that? How long would it take to get up to that speed if your acceleration was 9.8? Interesting. Okay, it's like your spaceship is falling through space and picking up speed at the same rate as something falling near the surface of the Earth. I mean, maybe that doesn't seem like an extraordinary acceleration. Like there are sports cars that accelerate faster than 9.8, but to do that for, days on end is quite a feat. So let's take a look. This is just, this only requires our simplest constant acceleration kinematic equations. Stop share. There we go. How many days? Well, let's break this down. We're given the initial velocity. You start from rest, so that's 0. We know the final velocity. It needs to be the speed of light. We know the acceleration, and we're trying to find the time interval for starters. That's part A. And you may get to a point after you've had some practice where you don't need to write down this stuff every time. It's a good idea to do it on an exam, again, so I can give as much partial credit as possible. But I'm recognizing that I can go straight to this one, the one that gives the change in velocity in terms of time interval and acceleration. Remember, you can only use this if your acceleration is constant, which it is, because we're told that it's a constant acceleration of g. The final velocity needs to be speed of light, which we denote with the letter c. The initial velocity is 0. The acceleration is that 9.8, and we're looking for the time interval. So all I have to do is divide g into the speed of light. Now, what we're doing here is something that would be common sense if the numbers were simple. For example, what if you're in a car, a sports car that's picking up speed at 10 miles per hour every second? So every second you're going 10 miles per hour faster. How long do you have to accelerate to get up to 50 miles an hour? The answer is 5, of course, right? 50 divided by 10 gives you the 5. So you know this intuitively, but when it comes to numbers that aren't so simple, maybe it doesn't seem so obvious. So you do want to resort to math. You want to use the equations. Well, we know that the speed of light is 3.0 to 2 sig figs times 10 to the 8th. What an obscene number. It's not infinity, though. And we divide that by the familiar free fall acceleration. Let me punch that into the calculator. And I find something like 3.1 times 10 to the 7th seconds. Now they're asking for how many days. I'm not interested in the exact answer, because what I'm recognizing here, here's a number that I have memorized because of astronomy. 1 year is about 3.15 times 10 to the 7th seconds. I have that memorized because the exponent I've memorized, and this number looks kind of like pi a little bit, right? It's close to 3.14, which is an approximation for pi. So evidently it takes almost a full year to get up to the speed of light, even if you're picking up speed at 9.8 meters per second. That's crazy, because 9.8 is a significant acceleration. We've already talked about dropping bowling balls off of tall buildings. Within a few seconds, you're going real fast. Imagine picking up that rate for an entire year. You still wouldn't be going the speed of light, although you would be pretty darn close. So that's an astoundingly high speed. Now, let's figure out how far you traveled during that time. So we have the same givens, although we've got an additional given now because we've already calculated delta t. And so I could add that to the list of givens, but I'm interested in how far. That's the displacement. And I'll go ahead and remind you that we do know the change in speed, we know the acceleration, and we know the time interval. Well, I'm recognizing I can go straight to this one now, which I call the 1/2 AT squared equation. It's your distance equals velocity times time equation modified to account for a constant acceleration. You've got that additional displacement that you'll go through because of your acceleration. I can cross this term out because we're starting from rest. And there it is. All I have to do is plug in numbers now. Because I've already calculated delta t, I'm able to use this equation. If I wanted to answer problem B first, before doing problem A, I would need, well, let's see. Is there another way we could do it? How about this one? V squared final minus V squared initial equals 2a delta x. Aha, we could also do it that way because we know the initial velocity is 0, we know the acceleration, and we know that the final speed is c. How about we just do this both ways as a check? So first method, I need to use SI units. Okay, the time interval I found was something like, it was actually more like 3.09 times 10 to the 7th. I square that. I've already got a huge number, times 9.8 divided by 2. And I'll call that 4.7 times 10 to the 15th meters. Whoa. Well, 10 to the 12th is already in the trillions. So this is what? 4.7 thousand trillion meters. There's not even a commonly used name for that. As a check though, delta x here would be v1 squared over 2 times the acceleration. Well, the final speed is the speed of light. So I'll put 3 times 10 to the 8th, square it, divided by 2, divided by 9.8. And of course I get the same number. Actually, because of rounding, my 10th digit is a little different. Okay, and I'll say compare in part C, they're asking us to compare that to 1 light year. Well, what is a light year? It's the distance that light travels in a year. So if I do this distance times time, I'm doing speed times time. Distance equals velocity times time, where I'm talking specifically about the velocity of light. I'm just imagining light traveling for a full year at constant speed. So that's 3 times 10 to the 8th meters per second. And I already gave that number for the number of seconds in a year. What was it, 10 to the 7th seconds? Yeah, I will be attempting to write more clearly here. I just need to remember 3 times 10 to the 8th times 3.15 times 10 to the 7th. So that's about 9.45 times 10 to the 15th meters. We'll check it out. Isn't this roughly half, very roughly half of that? About half a light year. Does that make sense? If you pick up speed at 9.8 meters per second for an entire year, we have seen that you get up to the speed of light, very close to it. And that means wouldn't that mean that your average speed for the whole year is about half the speed of light? So if you go at half the speed of light on average for a full year, you would have traveled half of a light year. So these numbers are all coming out consistent here. Now, if you're interested in this sort of thing, here's a way of thinking about that distance that's a little easier to memorize. 9.45 times 10 to the 15th meters. Well, I'm just going to round that to 10. And then I will use 3 of these zeros to turn meters into kilometers. Isn't 1,000 meters a kilometer? So this is now 10 to the 12th kilometers. So a light year is about 10 trillion kilometers, if you like to memorize things like that. Okay, now, here's another way of thinking about this. The free fall acceleration, we know, by definition, is the rate of change of velocity. Now, I would like to cast this in different units. The speed of light, well, you could say it's 3 times 10 to the 8th meters per second. Let me emphasize that's meters in 1 second. Or can't you say this? Doesn't it go 1 light year in a time of 1 year? By definition, a light year is the distance light travels in a year. So it goes a distance of 1 light year in a time of 1 year. Let's just do this. Let's define 1 year is the distance light travels in a year. So instead of calling it a light year, let's just call it a year. But we're actually talking about distance. This is something that physicists do in relativity because it just makes things simpler. Yes, we measure time in years, but we can also invent this new unit of distance called the year of distance. It sounds kind of silly and made up at first, but every unit of distance is made up, right? I mean, what the heck is a foot? Was that actually based on somebody's foot thousands of years ago? We don't even know who this person was. So all of these units are arbitrary. So a year of distance is by definition the distance that light travels in a year. It's a really big distance, right? A year of distance. So the speed of light is 1 year of distance is the distance, is how far it travels. Sorry, I'm being redundant here. It travels 1 year of distance in 1 year of time. And then you see that the units cancel. It's just 1. So by defining this unit of distance called the year, we're able to express the speed of light very nicely as just 1. And that means we can go up here and look at the free fall acceleration. We just saw that you can go, if you free fall at 9.8 meters per second for an entire year, your speed will increase by about the speed of light. So your final speed is c, your initial speed is 0, and you did that in a time of 1 year. And we've already seen that c, expressed in this system of units, is 1 year per year. travels a light year, a distance per year of time, and it does so in 1 year. Well, I'm talking about the free fall acceleration now. So those cancel, running out of space here. You see that we end up with just the number 1 and the units year in the denominator. So, and that's approximate because you saw all the rounding I did, but the free fall acceleration in SI units is 9.8 meters per second. In British units, it's 32 feet per second, but it's also what you could say is an inverse year, 1 inverse year. It looks really bizarre at first, but if you followed that discussion, what this means is if you're picking up speed at 9.8, your speed will increase by the speed of light every year. And the speed of light is 1 light year per year. So basically your speed is changing by 1 light year per year every year. 2 of those years cancel and we get this. I don't know. I've never had this, I've never met anybody else who thinks this is cool, but the fact that it's just a coincidence that 9.8 happens to be 1 inverse year expressed in those units is kind of fun. This next one is a little more challenging because we have to be careful with the way we set up the problem. If you choose notation well, a very clear notation, and you label things, it can go a long way in helping you conceptualize things or figure out how to set up the problem. So we've got 2 cars which are going to race. Now one of the cars, the Porsche, accelerates at a greater rate. Their accelerations are similar, 3.5 meters per second squared. It's not much greater than 3, but of course that could make all the difference in a race. So since they're only going 400 meters, the Honda is given a head start. Now, one thing we're not taking into account here is the fact that no car can maintain this acceleration forever. If you kept accelerating at 3 meters per second forever, what about just for 10 seconds? Or well, let's go with 100 seconds. Yeah. No, that's too high. 3 times 10. If you accelerate at this rate for 10 seconds, 3 times 10, that's 30 meters per second, which is over 60 miles an hour. And that's just in 10 seconds. So presumably after 20 seconds, you'd be going 120 miles an hour. And then 180 miles an hour. We know that cars cannot accelerate indefinitely. Now, can they maintain this acceleration for the entire time that it takes to traverse 400 meters? We're assuming that's the case. Because if they can't, that means we'd have to take into account the fact that each acceleration would decrease in time. That would be a much more complicated problem. So the Honda gets the head start. I think maybe the most important thing here is to figure out how you will define T0. So let's do that on paper. And let me take a look at these numbers here. 400, 3.5, Honda gets a 1 second head start. Okay. Stop share. Where's the screen share button? Let's label some stuff here. We know the displacement is, for both of them, 400 meters. The acceleration of the Porsche is 3.5. The acceleration of the Honda is only 3. Both of them start out with a velocity of 0. And we're supposed to figure out which one wins the race, right? Okay, well, if you try to do this in your head, you may have some success, but personally, I like to do it this way. T0 equals 0 seconds. So I'm defining the initial time T0 to be 0 seconds. That is when the Porsche begins accelerating. That's when they step on the gas. And so that would mean, I could even do this. I could say, let's see here. Yeah, I actually like the way, oh, pardon me. I like the way your solutions manual does this. Let's double up the subscripts here. I gotta start over. TP0. So this is the time for the Porsche. I'm going to assign 2 meaningful times for both for both cars, the time at which they start driving and the time at which they cross the 400-meter line. Those are the two relevant times, and I'm calling them T0 and T1. But those two times are different for the two vehicles. That's why we need the additional subscript. So TP0, that's the start time for the Porsche. And I'm going to go ahead and put that at 0 seconds because we do have an absolute coordinate system of time. And if the Porsche starts at 0 seconds, then the Honda, which gets a 1 second head start, would actually start at -1 seconds. So this all goes together. Sorry, this is sloppy, and we'll go with TP1. The Porsche crosses the finish line. Okay, and then TH0, that's the starting time for the Honda, and we've already decided that that's 1 second before the Porsche's starting time, so that would be a time -1 seconds. Honda begins, and then the unknown time TH1, that is when the Honda crosses the finish line. And in order to answer the question, which car wins, we basically have to compute these two times. What's the time at which the Porsche crosses the finish line? What's the time at which the Honda does that? Whichever one happens at an earlier time, that's the winner. Yeah, that's so surprisingly difficult problem, unless you're careful with the way you set it up. Now, which equation should we be using here? For each car, what are we given? Well, we know how far the car needs to go. It's the 400 meters. We know their acceleration. We know their initial velocity. And we'd like to find basically the time interval, right? What equation connects all of these variables? Well, that would be what I call the 1/2 AT squared equation. So for the Porsche, I can't spell Porsche. And I think I'll write the whole thing out, and it's all of its subscripted glory here. Delta X equals V naught delta T plus 1/2 AT squared. That's your general equation, but now let's write that specifically for this problem for the Porsche. Remember, delta is final minus initial. So the position of the Porsche at time 1, XP1, notice that the Porsche has this position at this time. It's at this position at the time at which it crosses the finish line, minus XP0 equals, and not just any old V initial, it's the velocity at time 0 for the Porsche times, let's see, T Porsche 1 minus T Porsche 0, right? It's delta T plus 1/2 acceleration of the Porsche times T Porsche 1 minus T Porsche 0 squared. So this is looking kind of ugly. Can we cross anything out? Both cars start from rest, so that term goes away. That's nice. Now, I didn't actually talk about my coordinate system here on the back. If this is my x-axis, x equals 0, why don't we just agree to put the starting point for the cars at the origin, and the finish line is actually at 400 meters. That'll be the easiest way to set this up. So delta x, final minus initial, that would be the 400 meters at the finish line minus the origin. So that's just positive 400. But before I do that, I think I'd like to solve, usually I like to do things algebraically. Should I continue to do that? I'm going to go ahead and plug in numbers at this point. So this is 400 minus 0, which is just 400. 1/2 times the Porsche acceleration of 3.5. And then remember the Porsche's starting time, we agreed, is when the clock starts at 0 seconds. So just TP1 squared. And fortunately, we didn't have to use quadratic formula because this term went away. And now I just solve for TP. I'm going to do this, the algebra in my head. I'll multiply 400 by 2, so 800. And then I'll divide by 3.5. And lastly, I would have to take the square root, right? And I get 4.78 seconds. So the time at which the Porsche crosses the finish line is 4.78 seconds. Now, you could have done it like this. for both cars, we know that the initial velocity is 0. So you could solve this equation for delta t. And that would be 2 delta x over a square rooted. Maybe that's a little clearer to you. But then you'd have to make sure to plug in the proper numbers. And at the end, you'd have to interpret this correctly. So I think for now, I'll just stick to doing it this way also for the Honda. So for the Honda, displacement, which is final Honda position minus initial Honda position. I'm just going to skip this term because both cars start from rest. 1/2 acceleration of the Honda times T Honda 1 minus T Honda 0 squared. So remember, this is the Honda's acceleration during this time interval. Now, what are these numbers? The Honda also finishes at 400 meters and it starts from 0. Just because it gets a head start in time doesn't mean that there's any change in the position. It still has to go through 400 meters. So 400, excuse me, this time is 1/2 times just 3.0. And here's where you have to be careful. This is the time we want. At what time does the Honda cross the finish line? That's by definition TH1. Don't be misled into thinking that that's also 4.78. TP1 is a different time from TH1. So this is still unknown. TH1 minus, but we do know the time at which the Honda starts. So we decided that that was -1 seconds. If you don't put the minus, then this will come out wrong. Minus is actually plus. So I'll write it this way, TH1 plus 1, and I'd have 800 divided by 3, and then I'd have to take the square root of that. What have I done wrong here? 800 divided by 3. Yeah, I forgot to take the square root. Okay, and that equals, hang on a second. Okay, I discovered my mistake. I don't know what the heck I was doing over here. That is not the answer. So I used the wrong order of operations or something. This is supposed to be 800 divided by 3.5. Then I take the square root. 15.12 seconds. Whoops. I'm sure many of you caught me making that error. If I round, I get this. Okay, so that's the time at which the Porsche crosses the finish line. And here I get 800 divided by 3, take the square root, okay, 16.33. So lastly, we solve for TH1, subtract 1, and that's 15.33. Okay, so the Porsche didn't win by much, but it did win. The Porsche got to the finish line slightly earlier than the Honda did, even though the Honda started 1 second earlier. Maybe you've got a different way of setting up this problem that makes more sense to you. I like this because you can look back and see very clearly how you defined your terms. So if you happen to get the wrong answer at the end, like I almost did, at least somebody could go back and look at your work and realize that you had some understanding about what you were doing. Next up is number 24 from chapter 2. This is also in your homework. This is the Superman watermelon problem, which must have been written in, 1950, because they're still using the Empire State Building as the iconic tall building. I think there are many taller buildings now. And I'm going to set this up a little differently from the way your solutions manual does it. It's nice to see it done a couple different ways. Remember, the solutions are all in the files folders on Canvas. So in this problem, somebody drops a watermelon off the top of the building. Not safe, because if that hits somebody on the ground, they're done. But we'll assume there's nobody down there. 320 meters below the top of the building is where the sidewalk is. And right when the watermelon is released, Superman flies by. But Superman, in addition to his other superpowers, defies gravity. See how it says Superman is headed straight down with a speed of 35? And we're supposed to take that as meaning his speed is constant. He's not going to speed up and speed up. So gravity evidently doesn't affect him. But the watermelon is in free fall, and it will be accelerating. And we're supposed to figure out when it passes Superman. So here's my lame drawing. I didn't get hired for my drawing abilities. Well, since the watermelon is released from rest at the moment when Superman passes the top of the building, Superman's going to be ahead of the watermelon at first because he's already moving at his speed of 35 meters per second, and it takes some time for the watermelon to pick up speed. Now, this picture is misleading. The Empire State Building is still pretty tall, so there's plenty of time for Superman to keep chugging along at 35 meters per second. Eventually, the watermelon will actually catch up because the watermelon keeps going faster and faster. It's accelerating due to gravity. So it should eventually overtake Superman, provided that the building is tall enough. So rather than do what the solutions manual did, I'm going to put the origin up here. So I'll say this is y equals 0, and I will call down the positive direction. Yeah. So that would mean that the gravitational acceleration, which also points down, gets a positive sign. The acceleration of this watermelon is going to be plus 9.8 because of my choice of coordinate system. Your book says up is positive, in which case the acceleration is negative 9.8. Both equally valid. They will lead to the same physical result. Okay, the acceleration of Superman is 0. The acceleration of the melon is positive g, where g stands for 9.8. The how about this? Velocity of the melon initially is 0, and velocity of Superman initially is the 35 meters per second. And let's define some times here. T naught, which is 0 seconds. So it's not necessary that your time labeled T0, it's not necessary for that time to actually be 0 seconds. That's just a name. You could pick 5 seconds as your initial time, but very often it's most convenient to set that equal to 0 seconds. That will be the time at which the melon is released. That's also the time when Superman passes the watermelon. Now, we're supposed to figure out how fast the watermelon is going when it passes Superman. So the first thing we should probably do is find out the time at which the melon passes Superman. Once we know the time, we could check to make sure that this problem makes sense. We could check where they pass each other, because if this is my origin and down is positive, this ground level would actually have a coordinate of positive 320 meters. If we find that the watermelon passes Superman at a coordinate of 330, that's below ground. That would imply that they both smashed into the pavement. So presumably, whoever wrote this problem picked the numbers so that they would catch up to each other before they get to a y coordinate of 320 meters. Okay, this time I think I'll skip the given and find. I suspect that this equation is going to get us to where we want. Delta y is v naught delta t plus 1/2 a delta t squared. That's our general equation, somewhat adapted to this problem because we're using the y-axis. But now, remember that delta y means y final minus y initial. And both of these two objects, Superman and the watermelon, they have the same initial coordinate. So y melon initial, oh, no, I haven't written this yet, is the same as the y coordinate of Superman initially. They're both at 0 at t equals 0 because I put my origin there on purpose. If you had put your origin here, then you would say that they each have an initial coordinate of positive 320. I kind of like this choice better. So this is y final minus y initial, which I can write as y final equals y initial plus v naught delta t plus 1/2 a delta t squared. This is the notation where, and I know this is kind of small, I'll write bigger. Y naught means the initial y coordinate, and y without any subscript means final time. So let me define my final time. I'll call it T1. That's when the melon passes Superman. Okay, so now my final and initial times are really T1 and T0 respectively. Let's apply this equation to the melon first. So the melon's y coordinate at time 1 is the melon's y coordinate at time 0 plus the initial velocity of the melon times delta t, and it's understood this delta t is really t1 minus t0 plus 1/2 times the acceleration of the melon delta t squared. I can cross this term out because of my choice of coordinate system. The melon starts out at a y coordinate of 0. I can also cross this term out because it's dropped from rest. So where is the melon at time 1? And now I can plug in the acceleration of positive g. And delta t is really t1 minus t0, but I conveniently chose t0 to be 0 seconds. So this just becomes t1 squared. So this is where the melon is at time t1. Its coordinate depends quadratically on t. Let's write the same equation now for Superman. Where is Superman at time t1, this time when they cross each other? Keep in mind, we don't actually know what that time is yet. That's the first thing we're looking for. So Superman's coordinate at time 1 when they cross each other or pass each other would be Superman's initial coordinate, which is 0 because Superman passes the origin at t equals 0, plus Superman's initial velocity, so velocity of Superman initially, times delta t, plus, we don't have to worry about the 1/2 at squared term. Oops, that's misleading. I shouldn't have crossed this out because it's not 0 for the melon, but you know what I mean. We don't have to worry about that term for Superman because Superman is not accelerating. All right, so we're left with just Superman's coordinate at time 1 is his constant velocity times, remember this is t1 minus t0, but I set t0 equal to 0. So I just get t1. And that seems remarkably straightforward. Why do I remember the book having to do a little bit more math? I think, yeah, you know what it is? It's because of the book's choice of origin. They put the origin down here. Well, you'll see what I mean in a moment. How do we solve for t? Well, the whole idea is that these two are at the same y coordinate when the melon catches up with Superman. So at time t1, these two objects must have the same y coordinate. In other words, the melon's y coordinate at time 1 has to equal Superman's coordinate at time 1. And that means that 1/2 g t1 squared must equal v Superman times t1. This is a very easy equation to solve because I can divide by t on both sides and solve immediately for t. The book wound up with something like this. They wound up with the quadratic equation in t, where the number b is not 0. This is not as easily solved. You actually have to use the quadratic formula in many instances. If it's not easily factorable. Factorable. So because of my choice of coordinate system, this coefficient b seems to have gone away, right? Because I can cross out this t1, and I can turn this power of 2 into a power of 1. It's, honestly, if you want to show your work on an exam or something like that, you probably wouldn't want to do this. Just write the next equation, which would be this. If I solve for t1, I would have 2 velocity of Superman over g. I sure hope I did this right. Superman moves at 35 meters per second, so 2 times 35. I divide that by 9.8. And I find that the melon catches up to Superman at a little over 7 seconds. That's a long time for this melon to be falling through the air. And I am checking to make sure that that's the same. Oh, what a relief. Same number that the book got. Okay, now what they're really asking is how fast is the melon going when it passes Superman? But before I answer that question, I'm kind of curious, does this actually happen before they smash into the pavement? I hope so. So I can check that real quick by plugging this time back into the equation for the melon's position at time 1. And let's see that the melon's position really is a y coordinate less than 320. That'll be easy. So 9.8. And here's something, 9.8 divided by 2, you're going to see that all over the place. 9.8 divided by 2 is 4.9. You might as well memorize that because it shows up so often. So 4.9 times 7.14 squared Okay. So they still have what is that? They've got 70 meters to go before they smash into the pavement. Plenty of opportunity for this melon to catch up with Superman. Okay, which equation can we now use to figure out how fast the melon is going? We want its velocity as a function of time. Remember this one? Change in velocity is acceleration times time interval. You can only use this for what type of acceleration? Ding, 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 constant acceleration. I've been hammering that point home for a while, constant acceleration. So this really says velocity final minus velocity initial. How do we do this? This is the velocity of the melon at time 1 minus the velocity of the melon at time 0. And this would be t1 minus t0, right? The time interval corresponds, the velocity at time 1 corresponds to time 1. Did that make any sense? Once again, we can cross this out because the melon is dropped from rest. So the velocity of the melon at time 1, well, it's picking up speed at a rate of 9.8 meters per second, and it does that for, we've now found, 7.14 seconds. Common sense equation there. So this thing's going basically 70 meters per second, which is 150 miles per hour approximately. That's a dangerous watermelon. You don't want to be standing underneath that thing. Okay, so this problem, it's some good practice with using correct notation. It seems to make things easier. Last one for this video, number 29 from the same chapter. Here's the one where we actually have to use that technique of resolving a vector into components that I talked about in a previous video. So we've got a snowboarder glides down a hill. That word glide and snowboard, I think, is supposed to clue us in to the approximation that there's no friction between the snowboard and the snow. We haven't learned how to account for friction yet, so we're keeping it simple. This hill has a small inclination, 15. Then she gets to the bottom and glides straight horizontally for 10 meters, then goes up a steeper slope. And we're supposed to figure out, first of all, how fast is she going at the bottom of the first hill? And then how far up the second hill will she go? So this is a great opportunity to use our constant acceleration kinematics. Here's my lame drawing. Here's the snowboarder. When they say a 50-meter long hill, they're referring to the hypotenuse here. If we were going to make a triangle, this would be the height of the hill and the hypotenuse. Now, the 10 meters is kind of irrelevant. Very often, the author will give you more information in the problem than you actually need. We're going to see it really doesn't matter at all whether it's 10 meters or 10,000 meters because we're not taking into account friction or air drag. So there's no reason she should be going any slower here than she was going here. Right? This is not really the time to talk about forces, but why is she picking up speed on the way down the hill? We know that's because of gravity. There's no mention of like wind or friction, so there shouldn't be any acceleration. That's kind of a subtle point that your book glossed over because this is a chapter 2 problem and the book has not yet talked about friction or air drag. Okay, as usual, let's pick some labels for times. We could say T0 starts down the first hill. T1, she reaches the bottom of the first hill. And again, you can solve the problem without being this formal because it's not real complicated. What we're doing here is not real sophisticated. We're just using the kinematic equations a couple times, but it helps. Again, it helps you stay organized with your writing, so you can go back and figure out where you made a mistake, or you can get maximum partial credit. So T1, she gets here. I might as well call this T2. Is when she starts up the second hill. And lastly, T3 would be when she comes to rest before sliding back down on the second hill. And because of my choice of subscripts, I don't think I actually need to write something like X0 the position at time 0. That's understood. Any quantities that have matching subscripts, we understand that those are quantities pertaining to those times. So on the way down, I'll use this marker here. On the way down, this will be my coordinate system. So that's the positive x-axis. And on the way up, that will be the positive x-axis. There's no reason I can't change my coordinate system for the two parts of the problem. All right, first let's figure out how fast she's going at the bottom of the hill. Well, we know her initial velocity. That really is the time or the velocity at time 0. That's understood to be 0. Since they don't tell us what her speed is at the beginning, we're just supposed to assume it's 0. She starts from rest. We also know the acceleration. That's that g sine theta. Remember that? I'll remind you of that. But we do know the acceleration. We don't know the final velocity. We do know the displacement, right? It's that 50 meters. And we'd like to find the velocity at the bottom, which is v1. You'll notice there's no mention of time here. So anytime you're doing a problem where the quantities you have and the quantities you're looking for don't include time, you should probably use this equation. v1 squared minus v initial squared is 2a delta x. And right now, this delta x means x1 minus x0, because those are the two times in question. The times when she starts down the hill and reaches the bottom of the hill. So remember this result from the previous video. If you've got a block, let's say, that's about to slide down a frictionless ramp, and this is angle theta, you can draw your g vector and then resolve it into components where this is also theta. So g is the full downward 9.8. This component is g sine theta. And that's what we want for, oh, it bled through it. I always forget about that. Sorry about that. That's what we want, is the acceleration parallel to the ramp, which would be g sine theta. In this case, theta is 15. So I can cross this out since she starts from rest, and I'll take the square root. V1 is the square root of, and I'm going to go ahead and plop all of this in right now. This is 2 times an acceleration of g sine, how about I call this theta 1? Theta 1 times delta x, which is x1 minus x initial. Right? This is root 2 times the acceleration times the displacement. And now I can plug in numbers. That's 2 times 9.8 times the sine of 15. And the displacement here, let's be careful. Since I've called down positive, this is really positive 50 meters. There's a displacement in the positive direction. And by the same token, since the acceleration we're talking about points down the ramp, I've given it a plus sign. This isn't negative 9.8 sine of 15. 50 meters. And don't be like me, don't forget to take the square root sign. Now, this is kind of interesting. Check this out. So we know that the sine of 30 is 1/2, right? Well, sine of 15 is 1/2 of 30, so maybe the sine of 15 will be roughly 1/2 of the sine of 30. In other words, 1/2 of 1/2 or 1/4. That doesn't work exactly, because if you look at a graph of sine of theta versus, so this is y, this is x. This is the line y equals x, this is y equals sine of x. For small values of x, those two graphs agree. Now, for the straight line, you can say that y is proportional to x, meaning if you double x, you double y. And that should also be true then for sine of theta, as long as you're talking about small values. So I'm just curious here. We know the sine of 30 degrees is 1/2. What about the sine of 15? Yeah, it's a little more than 1/4, a little more than 1/4. So that kind of works. It's not exact. You wouldn't want to make that approximation in general. Let's see how fast she's going. Times the sine of 15. Times 50. Hit equals first, at least on my calculator. Then you take the square root. 15.93 around it. Which is pretty quick. That's over 30 miles an hour. That's enough to really injure you if you hit a tree or something. So, snowboarding, skiing, I'm not going to think too hard. course, neither is physics, right? Okay, so we just assume now, this is where your book didn't really discuss this, but we're going to assume no loss of speed as she glides across those 10 meters. Now we're headed up. So I'll say up the second hill. And this time I'll be explicit. The acceleration is g sine 25 this time, but because of my choice of coordinate system, I'm going up the positive direction when gravity clearly points down the ramp. That's a negative acceleration. And now my initial velocity would be the velocity at time 2. My initial point, as far as this part of the problem is concerned, is at the bottom of the second hill. So v2 is equal to, that's the speed we just found. There shouldn't be any reason why that speed has changed during the horizontal stretch. And we know that the velocity, because we're trying to find how far up the hill she goes, right? Well, when she comes to rest before sliding back down, her speed is 0. And delta x, well, that means x3 minus x2. That's what we're trying to find. That's the unknown. You'll notice again, no mention of time. So let's go straight to this equation. Final velocity squared minus initial velocity squared is 2a delta x. And it's understood that this delta x is really coordinate x3 minus coordinate x2 in keeping with the subscripts that I chose here. And I'm solving for delta x. Can I cross any of these out? Well, when she gets to the top, her velocity is 0. So we've got negative velocity 2 squared negative v2 squared over 2 times the acceleration. Now you might be wondering, what's up with this minus sign? Because we know the displacement is up the hill, that's in the positive direction, and yet we've got a minus sign here. Don't forget that the acceleration is also negative. Those 2 minus signs will cancel. So here's where we plug in her speed from before. 2 times negative 9.8 sine of 25 degrees. And also a word of caution, you have to know how to switch your calculator between degree and radian modes. If you're entering a number in degrees, you better make sure that your calculator is in degree mode. 15.93 squared, where's that button? Divided by 2, divided by 9.8, divided by the sine of 25. And you'll notice I did repeated division there rather than, I don't like using parentheses in the calculator. It's easy for me to get lost. So for instance, A over BC, if you were going to enter that into the calculator, you'd have to say A divided by open parentheses, BC, close parentheses. I prefer to just say that's A divided by B divided by C. That's less number punching for me. Did I do this right? Have I hit equals yet? Yeah. 30.6 meters. That's how far up the ramp she goes. Now, does that seem reasonable? Because she slid 50 meters down the first hill, and now she's only going 30.6 meters up the second hill. You see why? This hill is steeper. So if she were to go another 50 meters up this hill, that would actually bring her to a higher point than the height from which she started. And something seems not right about that, right? Because she doesn't have a jetpack on her snowboard. There's no mention of that. And many of you who have already taken a physical science class, maybe you learned about gravitational potential energy in chemistry even. And so you sense that she starts out with a certain amount of potential energy that will determine the height to which she rises. She's probably going to end at the same height from which she started. We'll prove that later in the semester using a little bit of calculus. So let's check something. If we remember what I was talking about in the previous video, if you have a triangle like this, if you happen to know this angle and you know the hypotenuse, you can say that the opposite side is the hypotenuse times the sine of theta. Let's use that to figure out very quickly the height at which she started and the height at which she ended. So height 1, I'll call it height initial. I'm going to take the hypotenuse of 50 meters, multiply by the sine of 15 to find her original height. Excuse me. So 50 meter hypotenuse times the sine of 15. She begins at a height of 12.94 meters. And she ends at a height of, well, we just found that the hypotenuse is 30.6. She goes 30.6 up the embankment there. So 30.6 times the sine of 25 this time. I'll call that height 1. That's 12.93. The discrepancy, of course, is merely rounding error. So you could go back to the algebra I used and actually see this answer within what I did. Yeah, in fact, the formula that I used here, look at this. The distance up the ramp would be basically v squared over 2 times g sine theta, because the acceleration was g sine theta, right? Well, if I want to know the height at which she ends, I would take the hypotenuse, which is really the displacement up the ramp, and multiply by the sine of theta. Right? Hypotenuse sine of theta would be the opposite side of that triangle. That would give us the height. And now you see that those cancel, and that's just v2 squared over 2g. We could use that now and go back and show that that's actually the same as the original height. I don't think I'll do that, but if you trace the algebra steps backward, you can see that, of course, they had to wind up at the same height from which they began. So more on potential energy later. I will be working other problems from this chapter, and before we do that, we need to cover the ideas. We need to bring integral calculus into the discussion. We have to talk about how displacement is the area under the velocity curve. I can write that symbolically as this. Displacement is area under velocity, and that change in velocity is area under acceleration. So I'll introduce these ideas in a future video, and then we'll apply them to a few of the simple problems from your chapter 2 homework.